Hello everyone. In this video we'll be analyzing a rigid frame structure, an indeterminate structure in finite element analysis software Midas Civil. The objectives of this analysis is to calculate the bending moment diagram, determine the support reactions, and also see the deflected shape of the structure and see how the bending moment diagram correlates with the deflected shape. Now the structure is statically indeterminate. We have three pin supports and basically unknowns, six unknown reactions. The material properties of stiffness varies in the structure, so we have members such as AB and BD which have stiffnesses EI, and we have members BC and CE which have stiffnesses 1.5 times EI. So we will be seeing how the variation in stiffness affects the calculation of bending moments in the structure. We also have settlements at two supports. We have the support D settling by 3 millimeters, support E that settles by 2 millimeters. So let's see how to model this structure in Midas 7. So that's the blank window of Midas Civil, and we can go to File, New Project to start the new project file. Now make sure that this is a two-dimensional setting of the analysis. So we want to do it in XZ plane. Click OK, and we can also switch on the viewpoint so that it's clear which plane we are working in. So right now we are in the isometric view. I can change to the front view and we can see XZ plane is activated from the bottom right part of the screen. Units will work in kilonewton meters, so we select the units from the status bar, make sure it's kilonewton meters, or we can go to tools, unit system, and set it to kilonewton meters. Okay, so let's start by modeling the beams first. So we go to structure, base structure, beam, and let's see what are the dimensions. So it's 2 meters, 2 times 2 meters, then we have 4 meters and 2 meter lengths. So we will enter here 2, 2, 4 and 2 finally, and click add. Material and section, enter material as ID as 1, section ID as 1. So the default materials and sections will be assigned to these elements. Click OK. So the beam gets generated. Let's go back to the PDF, and now we will generate the columns out of the beams. So we have two columns, BD and CE. So the first column BD is 4 meters in height, and the second column CE is 6 meters. So we will use the extrude function to create the column line out of this 2 points here. So for easiness of selection, I'll display the node numbers. So basically node number 3 and 5 will be used. We go to node element, select extrude, make sure it's node to line, and we'll select using the select single option. So using this option we can click on node number 3 and enter the distance 0, 0, -4, so that will draw a column 4 meter in the vertically downward direction. Apply. Similarly we select node number 5. Okay, how do you know that this node is selected? We can see the numbers from the node selection box. So whatever node gets selected, the number for that node gets displayed here. So type in -6 this time and apply. So change to the front view again. So that's the completed structure. There is no pin joint in this structure. Everything is rigidly fixed. So all the connections are rigid. Okay, so let's now focus on the material and section properties. Now we have two different types of stiffnesses in this model. So we have one stiffness which is EI and the other which is 1.5 times EI. So for simplicity, we will assume that E is equal to 102.5 times 10 to the power 3 kilonewton per meter square, and we will assume I as 1 meters 1 and 1.5 respectively for the two stiffnesses. So that will cater towards EI and 1.5 times EI assumption for the stiffnesses. So let's define the material properties first. So properties, material properties, add. So our first material is a user defined material. We'll name it just E, and we'll enter the modulus of elasticity as 102.5 and 10 to the power 3, and click OK. So close this. Secondly comes the section properties, that is definition of the I, moment of inertia. So select add. Okay, so we will be entering a user defined moment of inertia which is 1 meter to the power 4 and 1.5 meter to the power 4. So selecting value type section, because in the value type section we can edit or enter our own section stiffness properties. Select solid rectangle, enter the name of the first section as I, and here we type in the IYY, because this moment of inertia represents the rotation about the y-axis, and that is what we are after. We are after the rotation or the moment calculation about the y-axis, the local y-axis of the element which is into the plane. So we select IYY and enter 1, and for the area we enter a larger value, so that if there is any deformation in the column, say the base of the column settles by some amount, then the top of the column will also settle by that much amount. So we are not taking into account the real stiffness of the column, rather we are more interested in the bending moment diagram. That's why we'll keep the IYY or the moment of inertia as accurate, but area we can play around with some higher value, so that we get the more accurate representation of the bending moment diagram without any other interaction of the actual forces or deformations due to the column settlement, etc. So we'll keep this as 100 area, and IYY is 1 meter to the power 4. Okay. We don't want any shear deformation in the beam, so we'll check this off. So we don't want to consider shear deformation in the beam, and apply. Then the same thing will repeat for the other material stiffness property, that is 1.5 times I, and just instead of 1 we'll replace IYY with 1.5 meter to the power 4, and that's it. Click OK. So these are our two section properties or two stiffness properties that we will be using. Switch to the works tree and you can find out that what section properties and material properties have been defined. Now you will see here that one of the section property 1.5 times I is marked in blue, whereas other is in black. The black represents the ones that have been assigned to the structure, and the blue is still unassigned. So we need to assign the blue or the 1.5 times I to the appropriate locations. So let's see where we need to define 1.5 times EI. So we need to define that on the members BC and CE. So use the selection tool. So we can create a window. We'll just create a window from right to left, so that you're just touching the two members here, BC and CE, and when you do that you can select or highlight these elements. Now once you have highlighted, you can simply drag and drop section number 2 or 1.5 times I, drag and drop and leave it in the model view. So drag and drop and leave it. So now you have defined the section properties correctly. So how to check that? You can obviously select, as we mentioned in our previous examples, you can select a particular section property, double click on it, and it will highlight all the elements that belong to that particular section. Double click on the section 2 and you can highlight the rest of the portion. Or you can also display the name of the properties. So you can go to display property and say property name, click OK, and it will show you the names of the different section properties. So I'll undisplay it now. Now that we are sure that it has been assigned correctly, we can focus on applying boundaries and loads on the structure. So the boundaries in this structure are all pinned supports. They are applied at 3 locations. So we are going to boundary, define supports. Pinned supports are defined by TX and DZ restraint, that is horizontal and vertical restraint, and no rotational restraint. So we can just simply select the nodes, just create a window around the node like this using the selection tool. And once you've selected, click on apply. So I'll just save the model as example 4 and click apply. So that's it. All the supports have been pinned and assigned to the right locations. Now I'll close this dialog box and we'll move on to applying loads. So for applying loads, we know that from the previous examples that we need to define some load case names to initialize the load assignments. So just enter a name using the static load case function, defining it as user defined, add, and close this dialog box. Okay, so let's see what types of loads we are looking at for this example. Okay, so we have point loads 16 kilonewton, 20 kilonewton vertically downwards at these two locations. Then we have a uniformly distributed load applied horizontally on the member CE, and we have settlement applied on the structure. So settlement is normally applied as a load on the structure, as a forced displacement, you can say, a specified displacement. So it will be applied as a displacement loading on the structure at the nodes on which we want the structure to settle. So let's start with the point loads first. So we go to loads, nodal loads, and use the selection tool. Select node number 2 and enter in the Z -16 and apply. Then we similarly select node number 4 and enter -20 and apply. Okay. Then for the uniformly distributed load in the horizontal direction, we select element and select this element by clicking on it. So you have selected this member, and the direction should be global X, is in the horizontal direction. The load is applied in the horizontal direction, maybe a wind load or any other lateral load. And in the W, we need to enter the value of that load. So I again go to the PDF and we will enter the value as 6 kilonewton per meter. So since the load is applied from right to left, we'll enter it as -6 and click OK. So that's the uniformly distributed load applied. Now we will look at the settlement. So we go to specified displacement of supports. So using this option, we can select the nodes which are going to settle. So first select node number 6, and it's settling, or deforming in the Z direction or vertical direction. So we select DZ, and let's see the value of the settlement. So support D settles by 3 millimeters and support E settles by 2 millimeters. So this one is support D, and we enter minus 0.003 meters, or this is 3 millimeters in the downward direction. Click apply. Similarly for the node number 7, we make it minus 0.002 and apply. So hence we have applied all the loadings on the structure. We can display the load values by right clicking on the works tree on the nodal loads, display, or on the element loads, display, or on the specified displacement, display. So it will display the specified displacement. All these entities can be edited using tables. So you can right click on nodal loads, go to tables and edit any value you want to edit. You can go to model view again, right click on specified displacement, tables, and you can edit the tables here. You can display the values in millimeters as well. If I go to millimeters, so that's the millimeters displacement values. Switching back to meters, then model view again, element beam loads, tables, that's the element number 6 applied with a distributed type of loading. Okay, so we have defined all the loads and boundaries. We can analyze the model. Analysis, perform analysis. Okay, so the model has been analyzed. I will switch off the node numbers for seeing the results. So we will start with results reactions first. Select fx, y, z. We are interested in the forces only, and furthermore the reactions, the supports will not include any moments because it's a pinned support condition. Select values here and switch on this box to enter the number of decimal points. Click OK, and you will find the results displayed in your graphical format in the model view. Okay, next thing, we'll see the deformations. So go to deformations, displacement contour, and you can click on deform, and let's say real deformation, and click OK. So that's the deformation of the structure. I can also click on undeformed to compare it with the undeformed shape. So if you see there is a faded gray line in the background, that is the undeformed shape of the structure, and the value of deformation you can find out here. So 3 millimeter deformation occurred at support D, and you can see the same occurs at the top of the column because the axial stiffness is very high, so the deformation effectively is carried over to the top of the column as the same deformation, and it will appear as if the top beam itself is deforming by the exact 3 millimeter deformation. Okay, you can magnify the deformations, so you can make it say 5 times for example. Okay, and you will find that there is a point of contraflexure over here. You can see there is a point where the shape of the displacement curve is changing. Okay, so now we'll shift to the forces beam diagrams, and let's look at the bending moment diagram. So my is to be selected for bending moment. Click exact and apply. Okay. So that's the bending moment diagram of the structure. You can click on min max to display the maximum and minimum values of the bending moment at different locations. Now here again you will find that the bending moment diagram changes its sign somewhere around here. If you remember, the displacement curve also changed the sign at this particular column around this location. So this gives us a kind of a comparison between the bending moment and the displacement diagram. They are almost they're taking the similar kind of pattern as you can see from the figure. Let us now see how we can correlate these results with the actual hand calculations. So I'll go to the hand calculation straight away. So since this is a statically determinate structure, we can't solve it directly um, using the three equations of equilibrium, that is vertical, horizontal, and the moment equilibrium. But we do have approaches, several classical methods like strain energy approach, moment area methods, and most recently the moment distribution method, which can be used um, to extract the forces, the the bending moment diagrams much easily. So in this particular example, we have used the moment distribution method. It's a very simple method which relies upon the relative stiffness of different beams at a particular joint. So what it does is, first of all, you have to calculate the fixed end moments for each member. So there are different formulas given in different textbooks for the fixed end moment calculation for different loading conditions for a member. And once you get the fixed end moments at each end of the member, you can start well, you can consider deformations as well into those fixed end moments. So you have equations for that which take into account the deformations, and considering those and considering the fact that you have relative stiffnesses, so you will calculate the distribution factor at each joint using the relative stiffness, and then a table is formulated which is also called the moment distribution table, and you will have the um, columns for each joint. So basically at each joint you are trying to balance out the moments, and whatever is carried whatever moment is unbalanced is carried over for the next iteration. So you repeat the iteration of balancing the moments until unless you reach a, a satisfied value of convergence, and you stick with the total moments then. So all these moments are then added up to get the final moments at each joint. And once you get the fixed end moment at each joint, you then separate out each member and draw a free body diagram for each member to calculate the shear force, the bending moment, etc., and say the deflections and all other things. So that's how we end up with a bending moment diagram using moment distribution method. And similarly, the reactions can be calculated once we calculate the moments, because we have the free body diagram for each member. And that's the deflected shape, which looks very similar to what we obtained from the finite element analysis. So from the distribution of from the displacement curve, we can make out which side or which part of the beam is under compression or tension. So for example, if you consider this portion, you will have the bottom of the beam in tension and the top of the beam in compression. So these are some comparison of results. You see the since the moment distribution method is an iterative analysis, so it depends a lot up to which step you want to continue doing the balancing of the moments. So that's why the results may not be as accurate as other types of analysis, but still fairly it gives you a good approximation of the results within the acceptable limits. So you have in Midas software, you have the moments, the reaction values slightly different from what we get from hand calculation. The difference is very little, but as I mentioned, the result difference is only because because of the statical indeterminacy. The the moment distribution method depends a lot on the number of iterations you want to do. So this concludes this session of indeterminate beam analysis. And for other examples of frame analysis and buckling analysis, stay tuned to our YouTube page, Midas UK. Thank you for watching. Bye for now.